what is Albert? So Albert is A light Bert. So what's new about Al? So as you probably guessed, A light refers to memory reduction. And so Albert is really bringing a memory reduction as well as a new pre-trained task. So we're going to start with the memory reduction. And so how vast is this memory reduction? We're going to first look at BERT large, which has 334 million parameters, and we're going to compare that with Albert extra large, which only has 253 million, or 235 million. So you're seeing about roughly 100 million parameter reduction. So now how does this magic happen? So two key additions: parameter sharing as well as decoupling the hidden layer size from the embedded layer size to let hidden really be as big as it should be. So first we're going to talk about parameter sharing. And so in BERT, if you have a 12-layer model, you're going to have 12 individual transformer blocks, and it's going to go through one after the other. And that's the traditional way. And what Albert does is fundamentally different, because instead of progressing through different ones, it actually just repeats on the same. So it's basically like a for loop or recursion going through. So if you have a 12-layer, you'll just repeat on that same block 12 times. And so next for memory reduction is decoupling hidden and embedded layer sizes. And so this is really to account for in-sentence context. So when you think about embedded, what's the purpose of embedded? Take words, become word vectors. But when you think about hidden, what's the purpose of hidden? It's to understand those case-by-case intricacies of that in-sentence context. And in this paper, they assume and they hypothesize that that's a much more difficult task, and that proportionally more memory should be spent here than on the embedded side of things. So now we're going to talk about how Albert improves accuracy from BERT. So in this changes with the pre-chain task. So a new pre-chain task. So as Aaron mentioned, there were two pre-chain tasks. The first one was MLM in BERT. MLM is mass language modeling. It's basically like fill in the blank or Mad Libs if anyone's remembers those good old days. The new one, the next one that you didn't get a chance to talk about was NSP, which I'm about to talk about now. So NSP stands for next sentence prediction. And so what next sentence prediction is given two sentences, does the second sentence actually come after the first sentence, or is the second sentence a random sentence from a different document? And this is more or less trivially solved with topic checking, which is basically, are those two sentences relevant? Do they share the same topics? And in this example, you can clearly see two sentences which don't share the same topic on the bottom. And so this is replaced with sentence order prediction. And sentence order prediction is basically given two sentences. The question is, did we swap them? And so this actually fundamentally increases the difficulty of the task, because instead of doing topic checking, now you have to do coherence checking. And this is kind of displayed to be a tougher task, because models that were trained to do sentence order prediction actually can do next sentence prediction, but models that were trained to do the previous pre-trained task, next sentence prediction, cannot do this new task, sentence order prediction. So that's interesting. So results of BERT and Albert compared on SQuAD 1.1. So you'll see that Albert actually comes out on top with a half point increase, roughly half point increase across the board. And this is impressive on its own, but what's more impressive is this is a light BERT, so it's actually doing it with about a third of the memory. So that's really important, really impressive. Now let's move on to the next dimension of question answering, SQuAD 2.0. So what's new in this data set? So now that we've been able to more or less beat human proficiency with answering, reading comprehension, when you know that the answer is within the passage, what about when the answer isn't in the passage? How do these models know when they don't know something? And so what they did is they added 50,000 new unanswerable questions to SQuAD 1.1's 170,000 answerable questions. And so here's an example of an unanswerable question. So Aaron and Alex are the best of friends. Aaron is at the park and Alex misses him dearly. So what's the question is, where is Alex? And the correct answer is, well, Aaron is at the park. Alex misses him. We don't know where Alex is. So the correct answer is no answer. So how do these engineers and researchers evaluate what a good unanswerable question is? And so they used relevance and plausibility to force a deeper NLU. So with regards to relevance, it's pretty straightforward. is the unanswerable question relevant to the passage? Do they relate? And so this is an example of an irrelevant question, an unrelevant question. What I changed the question to say, where is Jeffrey? And Jeffrey is an entity that's never mentioned in the passage, and therefore it's kind of simple for an algorithm to say, yo, Jeffrey was never in here. No entity recognition of Jeffrey. This is fake news. We don't know the answer. So plausible. Now we're going to talk about type checking. And so when you think about types, every question has a type, and that type is based on the return type of the answer. So if you think about, for example, how tall was he? You're looking for a height back. If you talk about what do you want for dinner, you're looking for a food back, a meal back. So you're looking for so answers or questions have answer types. And so when we look at this question, I revert the question back to the original, where is Alex? And where implies that we're looking for a location. And so we've sneaked in a little park right next to Alex. Even though they're unrelated, Aaron is at the park and we don't know where Alex is. There's a location located right next to the entity Alex. And so that is kind of like bait. It's a plausible answer to show that there is a location. And now really the task of the model is to identify that there is no relationship between those two entities. So looking at SQuAD 2.0 results for Bert and Albert, there's actually a full point increase. So the gap has doubled from SQuAD 1.0 or SQuAD 1.1 to SQuAD 2.0. And I believe this is because they swapped NSP for SOP, next sentence prediction for sentence order prediction, because sentence order prediction focuses on coherence and NSP focuses on some topic checking, which is mostly irrelevant in this case. So now analyzing retroreader, this is our final paper. And so the retroreader paper argues that these new question types in SQuAD 2.0, these unanswerable questions, have two fundamental parts. Number one is begging the question, are these questions answerable? And the next one is, what is the answer? And previous papers have found that the best way to solve this is by adding a verifier. So the verifier is meant to verify the answerability. And this paper argues that previously the verifier has been placed kind of carelessly, and the goal of this paper is to really add some care and cleverness to the placement of the verifier. So we're going to take a quick detour and talk about a paper that isn't about NLP. It's actually about how to read research papers. So I've never really read research papers. This is my first time reading research papers. And so someone mentioned, there's a paper about how to read research papers. So I read that first, and the algorithm it gave for, young researchers trying to learn how to read research paper was, number one, do a sketchy pass, where you look at abstract, intro, and conclusion. Number two, do a second pass, which is an intensive pass, which is everything but math. And finally, a pass 3 for proofs, which is just the math. So now analyzing retroreader, so I read that pretty much right after reading how to read papers, and I was kind of like, this is deja vu, because retroreader actually has a human-inspired two-pass verifier architecture. So at the top here, you'll see there's actually a sketchy reading module, and then there's a more intensive reading module underneath. So it's got a two-pass, exactly how to read suggests reading. It's built on Albert. So talk about the first pass. First we have input, embedding, encoding, and answerability score. And this is pretty common stuff. Ultimately, it predicts that the answer is just kind of vaguely in the passage. Next, you have the second pass, which is the intensive pass. And what's added here is a span prediction. So what span prediction does is actually looking in the passage and making a prediction about answer candidates, and then it's finding whichever one's the most likely answer candidate, and now it's taking that. And so when you're looking at this answerability score, it's just answering if this candidate, the most likely candidate, seems to have the answer within it. So it predicts the answer if the answer is in the candidate span. Now both of those scores from the sketchy and the intensive are merged together in the rear verifier. And so there is a threshold system. So if your scores, when they're amalgamated to get a V-score, a verifier score, if your verifier score is above a certain threshold, you're going to abstain from answer. You're going to answer no answer. And if they are below the threshold, you are going to return your candidate answer. So now let's take another look at SQuAD 2.0 results. And so you have human performance, and all of these are well above human performance. And if you notice, most of them have Albert Most papers have Albert in the name, and then you have Retro Reader, which also has Albert, and that's the paper I just told you about, placed at second. So in conclusion, question answering today, transformers are on top. Question answering tomorrow, transformers augmented by psychology and humanoid-inspired modules. That's where things are going. So hope everybody learned a little and hope everybody had fun. Thank you for your time. These are our sources. And are there any questions? Thank you.